Okay. Right. Hi, everyone. Thank you for joining us today. We are on the 7th of August, and today we will be starting off with some updates on the APAC Scientific Forum that G1 will be giving us. And then we have our Korea team. We have Subin here, who will be sharing about the CDM for oncology and AI-empowered clinical oncology data structure. Yeah. So with that, I'm handing over to G1 to get us going. Thanks.
Okay, thanks, Mukesh, for letting me hop in and talk a bit. And before we start, before we dive into Subin's presentation today, I just want to briefly share about the upcoming APAC Symposium. And okay, let's start with where and when. And as many people here already knows that 2025 APAC Symposium will take place on December 6 to 7 in Shanghai Jiao Tong University in China. And I've never been to Shanghai before, but I'm not sure I could attend this symposium this year. But yeah, the beautiful city. So everyone, please join the symposium this year. And here's a quick look at the timeline for collaborator showcase. Abstract submission is open from August 4 to September 7, which is already open. And after that, the scientific committee will review the submissions, and then notification of acceptance will open on October 17, and the main event will happen in the first week of the December. And just a heads up, the registration will be announced soon, so stay tuned, please. And also, if you're planning to present, the brief report submission is now open, as I just mentioned before. So you can just scan the QR code right here, or you can just go to odyssey.org website and click the landing page right here. So yeah, and that's it. And this year's symposium is quite compact, just 2 days long symposium. And here's what 2 days will roughly look like. Day 1 is about tutorials about the introduction of Odyssey and OMOP CDM and vocabulary and ETL and analytics as usual. And day 2 shifts to the research updates and presentations, which will be Odyssey, APAC, and regional chapter updates, and 2024 APEC studies from China study teams, which will be Fudan University and Beijing University and USDC. And real-world data development in China, their use cases will be also present. Will be also we're considering to see some real-world data developments in China too. And plus panel discussion from OMOP and non-OMOP panels. And the poster sessions will be also present. So lots of opportunity to connect and learn from each other, I think. And yep, that wraps up my part today. And yeah, that was really quick. So, and yeah, thanks to Mukesh again. And now I think I'm going to toss the stage back to Mukesh again.
Thanks, G1. Yeah, so do give us your support for the Odyssey APAC Symposium that's happening at Shanghai. All right, we will now move over to Subin, who will be giving us her sharing on the CDM for oncology and using AI for the oncology data structure. Over to Subin. Thanks.
Thanks, Mukesh. Yeah. Oops. Yeah. Hello, everyone. I'm Subin Kim from Yonsei University in Korea. I'm currently working in Professor Chang's lab. Today, I'm going to talk about the Oncology CDM, which has been proposed by the Oncology CDM working group, and how we can leverage generative large language models to process unstructured cancer data. Before we dive into the main topic, let's first talk about why we need an Oncology CDM. There are several key challenges when applying the standard OMOP CDM to oncology research. The first problem is granularity. most common conditions are defined by three components: morphology, site, and cause. However, cancer is somewhat different. It needs more detailed information, including grade, size, and biomarkers. These are very essential when we implementing cancer research. For example, let's assume that research question is, what is the progress-free survival of patients with metastatic non-small cell lung cancer with confirmed MET exon 14 skipping who received oral capatinib as first line? We often need like this detailed information, including genetic mutation and metastatic information and line of therapy, such as whether it's first line or not. Unfortunately, most of these details are not directly captured in the standard OMOF CDM. The second challenge is the complexity of chemotherapy. Unlike common treatment, chemotherapy is not a single drug administered once. It's a cycle-based and often personalized treatment plan. So patient might receive a combination of drugs in multiple cycles over weeks or months. So, for example, consider FOLFOX regimen. This is a common treatment for colorectal cancer patients. It includes a combination of these drugs, fluorouracil, leucovorin, oxaliplatin, and typically administered in multiple cycles. The standard OMO CDM is able to capture these individual drug exposures at the ingredient level, but unable to represent this regimen and cycle. Third problem is lack of episodes. We want to track patient journeys, but this is sometimes not supported in source data. So without episodes, we cannot easily track patient journeys like time to progression or time to remission. So to address these challenges, Oncology Working Group proposed the Oncology CDM extension. They introduced these three major models: cancer disease, cancer treat, and cancer episode model. Some of you guys may already be familiar with these models, but for those who are new, I'll briefly explain one by one. First one is cancer disease model. This is for linking of base diagnosis and multiple diagnostic modifiers. So what is base diagnosis? Base diagnosis is for cancer is combined with topography, location, and histology. And diagnostic modifiers include things like staging, topography, histological pattern, dimension, and biomarkers. For the base diagnosis, we use the ICD-03 code, as this code combines histology and location. Generally, we use ICD-10 to define condition and diagnosis, but this only provides the location of cancer. So with ICD-03, we can know the histology and location of cancer. So this is an example of how the base diagnosis is stored in condition occurrence tables. Condition concept ID is mapped to an OMO concept ID for ICD-03 code, and condition source value contains ICD-03 code itself. And next is diagnostic modifiers. To represent cancer-specific modifiers, Oncology CDM developed a dedicated vocabulary called cancer modifier. These modifiers, such as tumor grade, stage, or biomarker nodes or metastasis, are stored in the measurement table of the CDM. And Oncology CDM extension proposes new columns in measurement table, these two columns, and these two columns allow us to create link between condition cross table and measurement table. Second is cancer treatment model. In the OMO CDM, treatments are recorded in drug exposure tables and procedure occurrence tables. These tables can store information like a single surgery or a drug that was given to the patient. While these information were sufficient for general treatment, The drug exposure and procedure occurrence tables are not sufficient for regimens that required for cancer treatments. To integrate regimen in the OMOP-CDM, working group integrated hem-onc ontology for regimens into the OMOP standardized vocabularies. When you search for folks in Athena, you can see the standard concept from hem-onc ontology. Also, you can see that for folks is mapped to individual regimen components, standard RX known concepts of fluorouracil, leucovorin, and oxaliplatin. Third one is cancer episode model. This model is designed to capture the patient's clinical journey from the initial diagnosis to treatment and outcomes. So what is episode? Episode is continuous periods of disease or treatment that have clinical meaning. For example, this could be a progression phase of the disease or treatment regimens. So why do we need them? Because they allow us to capture and understand the patient's journey, such as progression-free survival and time to progression. So Oncology CDM working group introduced a new table, a new logical model called episode table, and respective concepts into the OMOP CDM. One of the example is disease episode. Disease episode can be recorded in this table. So these episodes are structured into parent episode called overarching disease episode, and this is extent, and this is dynamic. Overarching disease episode covers the entire cancer duration, like incident of a cancer to last follow-up or death. The disease extent describes the spread of the disease, and this is dynamic, reflects how the disease is behaving over time. This is a real-world example of how these episodes can be structured. The patient was diagnosed with bladder cancer, and the bladder cancer was recurred, and there was long metastasis and passed away. These clinical events are grouped into overarching this episode, and the changes like metastasis can be structured like time to metastasis as extent episodes, and dynamic episodes for disease progression, like recurrence of bladder cancer. Yeah, the oncology working group proposed valuable CDM extensions for oncology research, but in practice, there are still many challenges in implementing these CDM, especially with EHR data. The biggest issue is that cancer-specific information is often unstructured in EHR. They are usually found in clinical notes like pathology or radiology reports. This makes it difficult to extract and standardize the oncologic data. Conventionally, supervised artificial intelligence was used to extract data from clinical notes, but recently, generative large language models like ChatGPT have been actively used to extract cancer-related information from the text. Based on this idea, we introduced an NLP pipeline that leverages generative large language models to extract cancer-related data from unstructured pathology reports. The pipeline consists of 3 main steps: parsing, extraction, and structuring. For the parsing and extraction step, we use open source model Gemma 3 from Google to process the clinical text and extract cancer-specific information. Let me briefly explain about this first step. Parsing step, we classify the entire pathology report into 4 domains: finding, lymph node, biomarkers, and others. This is the example. So you can see that this is a raw original pathology report, and this is the output of stage 1. The pathology report divided into finding, lymph node, biomarker, and others. In finding there are tumor-related features are stored in this finding section. Yeah. And next is extraction step, where we extract cancer-specific modifiers from the first pathology reports. Before we begin the extraction process, we first need to define which clinical variables to be extracted. As a baseline, we refer to the CAP cancer protocol, which provides standardized reporting elements for pathology. In addition, if the report contained information relevant to TNM staging, we include those variables as well in the extraction targets. Here's the detailed example of the variables we extracted for colorectal cancer patients. Based on the CAP protocol, we defined 25 variables to be extracted, such as dimension, depth of invasion, margin status, and invasion status, and lymph node. Also biomarkers, yeah. And this figure shows an example of the prompt we used for information extraction. For each category, we predefined set of option values for the target category. The model was then instructed to extraction information within these predefined options. And this is the example of stage 2 output, extraction steps output. For each category, you can see the model extracted a specific answer based on the information in the first pathology report. You can see that in the original pathology report, the procedure is recorded as laparoscopy-assisted anterior rejection, so model extracted the answer as anterior rejection. And the model did pretty well done, yeah. And apart from the answer, model also extract evidence and confidence. Sorry. Yeah, the confidence is represent how certain the model is about the answer they generated, and the evidence shows the part of the test that supports the answer. The last step is structuring step. As the output of stage 2 is JSON format, in this step we convert them into the table format. This makes it much easier to map the data to the OMOP CDM. And this is the example of structuring step. We converted JSON format into table format, and you can see that it is well organized. This is our preliminary result for NLP pipeline. We randomly sampled about 100 pathology reports for each cancer and ran our pipeline. We can see that model showed considerably high performance across three types of cancer. And after structuring the extracted data, the next step is to map each value to almost standard concept. For example, a term like adenocarcinoma would be mapped to a standard OMO concept ID. For each category, we first determine the appropriate domain and vocabulary. For example, if the category is dimension, we will use cancer modifier vocabulary. After that, we created a mapping dictionary that links our possible outputs to the standard concept ID into the OMO CDM. Yeah, now I'd like to talk about how we are handling the ETL process. First, we connect the procedure occurrence table to node table so that each pathology report can be matched to the procedure. And this is the NLP result table. This table contains the output from our NLP NLP pipeline. Based on that, we populate the node NLP table. So the category from NLP result, lymphovascular invasion goes to section concept ID of node NLP table. The answer value is mapped to node NLP concept ID. After that, we pass this information into the measurement table. The section concept ID goes to measurement concept ID in measurement table, and node NLP concept ID goes to value as concept ID. And finally, to indicate that this record is from NLP analysis, we set measurement type concept ID to a concept that represents NLP. Let me show you an example ETL case. This is a pathology report from a patient with colorectal cancer. The pathological diagnosis of this patient is adenocarcinoma moderately differentiated, and the largest dimension of carcinoma is 5.5 centimeter. On the left, we have the NLP result table, and you can see that the category histology type is mapped to section concept ID of node NLP table, and the extracted answer, adenocarcinoma, not otherwise specified, will go to node NLP concept ID in node NLP table. After storing the extracted information in the node NLP table, we move on to mapping the data into the measurement table. As you can see here, the section concept ID from node NLP is now used as a measurement concept ID, and node NLP concept ID goes to value as concept ID. For measurement type concept ID, we stored 32858 to represent it is from NLP analysis. And if the answer is number, like largest dimension of tumor, we use lexical variant column in node NLP table. This column is for raw text extracted by the NLP tools according to ㆍCDM 5.4 conventions. And the lexical variant from node NLP table mapped to value as number in measurement table. Yeah, so now let me wrap up with take-home message. First, cancer research needs a much more granular and structured data. The ㆍCDM, the Oncology CDM addresses this by introducing detailed models for cancer diagnosis, treatment, and episode. However, it is difficult to extract data from unstructured clinical notes, especially in EHR data. So by using generative LLMs, we can extract cancer data from clinical notes. And finally, with the ETL pipeline, we can transform extracted values into a standardized format that fits into the ㆍCDM. Thanks for listening, and I'll be happy to take any questions.
Yeah, thanks, Subin, for that. I think it's a great sharing there. Maybe I'll start off with a question around Gamma. So I think you showed it very nicely using Gamma 3 to extract the unstructured data. How do you handle the data privacy issues? Were you having a local version of Gamma 3 and running this locally? How was this done? Yeah, thanks.
Yeah, we downloaded Gamma and ran in the local environment, so we can prevent the problem from privacy. Yeah.
Okay, thanks. I think we have a question from Lynette. Yeah.
Hey, I just had a question about the confidence score.
Yeah.
I'm not sure if you mentioned how it was derived. Yeah, just wanted to know about that.
Oh, yeah. Okay. So in stage 2, model gives us the confidence. This is just the confidence that selected by models. 0 to 1 scale, and after that, we will use this score to filter out low confidence answers and use to manually check that it is right or wrong. So
okay.
this is just model's output. Yeah.
Okay. Thank you.
Yeah.
Thanks, Lynette.
Yeah,
Jiwon?
I have a question. Thank you, Subin, for your presentation. It was really great. And my question is really related to Lynette's question. It was about the confidence score. Do you have any threshold for the confidence score? Like if the score is like 0.7 or 0.6, like what are you gonna do? Like do you still go ahead and use it, or you just manually check it? And is there any standards with the confidence score?
There are no standards, but we will check the overall distribution of confidence and use median or some threshold to define which is low confidence.
Okay, thank you. And the result was really good, right? The accuracy and that score, like,
Yeah.
the result, accuracy and precision was.
Yeah, it's just preliminary result, but yeah, it's considered really high. Yeah.
Okay, thank you.
Any other questions from the audience? Cynthia, I think Cynthia has a question.
Thank you for this excellent presentation.
Cynthia, we can't hear you. Your voice is really small, so we can barely hear you.
Is it better now?
Yeah, so much better.
Okay.
Yeah.
All right. Thank you very much for this excellent presentation. I'm wondering about the drug regimens. Are there certain drug regimens, like I remember one in the past that I would hear about, like ㅍ. Are those now like a single standard concept ID, or you still have to list the drugs individually?
Actually, I'm not well known about
I think
regimens. But
let me answer
okay.
your question, Cynthia. So, as you asked, kind of there are numerous regimens, just like ㅍ, and all of these, not all of this, but many of these are captured in HemOnc vocabulary. So we built a new vocabulary like HemOnc, and individual drugs as well as this, grouped regimen are captured in Oncology CDM right now.
Yeah, and in the HemOnc, it is mapped to arsenal ingredient level. So yeah, you can connect it them.
Okay, and so that hierarchy is built in.
Yeah.
Okay, thank you.
Ichu, I think Ichu question. Yeah.
Hi, I have a quick question that you just saw us the result, and I saw that the accuracy of lung cancer is quite low than others. So, do you have any thoughts about why the lung cancer has a little bit low accuracy?
I think apart from other cancer types, lung cancer have multiple specimens, and in my memory, the lymph node, the name of lymph node is quite complicated. I think that influenced the results.
Thank you.
Got a question from Yang Chi.
Yeah, very good work. Are you able to populate the episode tables, for example, the progression episode?
Yeah, we are trying to populate episode table using cancer registry and EHR data, but it is quite difficult. Yeah.
Okay.
Yeah.
So basically, we do have two different data sources in here. One is EHR, and the other one is cancer registry. So just like SEER, we have to report our, the history of cancer patients individually to the kind of national surveillance system. So we leverage that system to populate to capture the progression or the final results of the cancer in the patients.
Okay, so how do you define progression then? Like, is it tied to individual cancer, or is general? You have a systemic way to populate it.
We are
I'm not
planning. Yeah.
actually 100% sure, but I think that if we find the progression, and then usually we have to change our treatment pattern, treatment options for the patients, and then we have to report that. So before changing the treatment, usually the hospital reports the progression. I'm not sure that the actual process. Subin, do you know more that this?
And I think we can use radiology reports, because in the radiology reports we can see the changes of size, like size is bigger or size is progressive. So we can use radiology reports also. Yeah, but we have to try. Yeah.
Okay, thank you.
I've got another question around the speed of extraction for gamma. Do you have like a rough rate how long it took for you to process the unstructured data?
Also, how much times for one pathology report? Stage 1 is pretty short, maybe 3 or 5 seconds for one pathology report, and maybe in stage 2 we should spend almost 30 seconds to extract one pathology report.
And one pathology report, how long is the length of it? A typical report?
It is case by case, but yeah, usually looks like this.
Okay.
Yeah.
Okay. Yeah, that's not bad actually. 3 to 5 seconds. Yeah.
Yeah.
Right. Okay. Any other questions?
I just have overall question to Subin's research, because I love to ask people's experience and their insight. Were there any challenges you faced during this doing like OMOP CDM extension, Subin? And any
there's many challenges I face. Like I had to develop prompt strategy. It is one of the difficulties, and biggest challenges was the lack of clear conventions when we are doing ETL process. So sometimes we have to make decisions on our own. Yeah, so we are planning to discuss those complicated cases with Oncology working group when we organize all of that. Yeah.
In terms of Odyssey APAC, the one of the fundamental limitation or challenges that that communicating with other parts of the world. There is an oncology worker, but their meeting time is very hard for us to participate. So it's very hard to communicate with them simultaneously. And then another challenge is that while we are building this oncology extension in our institution, we cannot guarantee that it can be expanded across the world or across the regions. So, I hope that other institutions to start to work on this, to expand the oncology data across the Odyssey network.
Cool.
Yeah, I echo Chen's comment. We have the same question, like particularly for the disease dynamic episode. How do you define a stable disease? How do you define a progression? Those, I don't know whether there's any consensus among the members of Odyssey. Let's say we define one, whether it can be used as a network study for other groups, because they may disagree with our definition and the parameter or the value we use to define those. So that's the challenge we're facing. So
yeah, I truly agree with that. But I think I'm not sure because I'm a little bit apart from the oncology work group right now. So, but I think this is one of the most comprehensive experience for oncology work, oncology extension, actual implementation of oncology extension model of ㅍCDM. So we faces lots of challenges, and we have to define lots of things in actual implementation. And so that's why, once again, I hope that others to participate in this, because if so, then we can discuss the more detailed conventions or definitions around this oncology extension model. But that is truly, really great comment. Thanks.
Cynthia?
I think it's like the oncology profession, and the different subspecialties that define progression or stable disease. So I don't think it's something that, Odyssey has to define.
Yeah, indeed. Yeah.
yeah, but they actually have it in their wiki page, so they have a logic which not everyone agrees. Like say you had a surgery, like a resection, right?
Mhm.
They treat that as a remission. So so that's why it's in the remission episode. So it starts with if you look at the wiki page, I think it's remission. I forgot it. I could be wrong, but in the wiki page, surgery triggers an episode actually, and not many people agree with that. So,
but is it maybe in the clinical note where it would be written that the oncologist says, it's now in remission?
no, the surgeon will not put those as a remission. The surgeon will, the tumor get cut, right? It's
Right.
Whether that's defined as remission, the surgeon will never define that as a
Right,
remission.
right. But the
It's
oncologist, I'm wondering about the
not the
oncologist.
oncologist. Oncologist, I don't think so. Not based on my experience, though.
Yeah, I wouldn't think of that. Remission usually means like some disappearance of the cancer. Interesting.
Yeah.
I would think that we should just rely on what's in the actual record. But since I'm not party to all those discussions, I shouldn't really, comment too much on the robust discussion that's occurred.
Just what Key and Cynthia and Chan mentioned, like it seems like it's really hard to make a like consensus, right? So it's hard to align everyone into one. So like if I can add one more question to Subin, like in your opinion, what should be prioritized as a future direction to help to address this kind of issue? Like, is there any, maybe Chan can answer? I don't know. I'm not a professional
What
here,
is the
but
what is the
yeah.
question? What's the future?
Future
Um,
study?
The actual what is the actual
question? Oh, yeah. What should be prioritized as a
Okay.
future direction to make a consensus?
So, it takes more than 2 or 3 years to define the first proposal of oncology extension model at the first time, and then until now, not a single institution implemented this oncology extension model very comprehensively. We theoretically define the conventions as Keith said, but no one to my knowledge, no one actually implemented that all. So we have to try to implement that conventions with the actual real world data, and then we can discuss about it more. So the first step should be implementing with the actual data.
Okay, so you guys are pioneers.
I think so. I'm not sure, but I think so. I've not participated in oncology work group, so I did not know much about that. The current landscape of oncology work group in Odyssey.
Thank you.
Yeah, thanks. And I think in Singapore as well, we're getting started on the cancer registry work in terms of harmonizing to ㆍCDM. I think a lot of the work that Ken and team have done, we can definitely collaborate to see how we can build upon it. Yeah. Okay. We are 11:42. Any other questions that we have in the audience? Looks all good. Yeah. Thanks again, Subin, for the wonderful presentation. If not, we will come together again 2 weeks' time for the community call. Yeah. Thanks, everyone.
Thanks, Mukesh. Thanks,
Yeah,
everyone.
thank you.
That's Mukesh.
Bye-bye.
Thank you.
Bye.
Bye-bye.